Good morning. My name is Evellin, and I will present our work on intelligent helmet that use IoT to improve safety in industrial environments. This project was developed at the State University of Ceará. I'll structure this presentation in five main parts. First, the context and motivation behind this work. Then, our proposed solution, the methodology we used, and our experimental results, and finally conclusion in future directions. Occupational safety remains a critical challenge. In 2024 alone, Brazil recorded over 742,000 workplace accidents and 2,400 deaths, despite preventive measures in place ties in industrial revolution. Traditional approaches are insufficient. We need intelligent, automated solutions that can detect situation in real time. Technologies like IoT, AI, and decision-making methods have emerged as essential tools to address this problem. So our solution proposed are integrated IoT and wireless-based architecture made of monitor helmet and mobile station. The key innovation lies in combining video communication protocols, lower for long range, low power critical data, and Wi-Fi with WebSocket for high bandwidth video streaming with entropy-based risk detection. This approach ensures stable connectivity and low latency even in challenging industrial environments. The system architecture consists of two main modules. The monitor helmet collects data used in integrated camera for video, a gyroscope and accelerometer for pathway and fall detection, and an infrared sensor to monitor eye movement and detect drone scenes. The mobile station receives puts together and displays this information in real time for the safety team. All data is stored in a SQL database for possible historical analysis and report as generation. The workflow begins with data collection at 100 millisecond intervals. The helmet preprocessing the data locally to optimize transmission. Communication used lower for critical safety with long range and low power use, while Wi-Fi with WebSocket handles video streaming with minimal latency. The risk analysis modules run all the time, identify situations like falls, from signs, and abdominal posture shifts. All information is displayed in real time in storage for the future analysis. And in the methodology, we conducted controlled experiment with team volunteers, performing activities that simulate typical behaviors in work environments. These include drum simulation, walking in different postures like standing, sitting, and lying down. Tests we performed in both indoor and outdoor environments to validate the system under different real-world conditions. Data was sampled every 100 milliseconds for all sensors. And the innovation is our entropy-based risk detection approach. Entropy shows the unpredictability on handleness in sensor data. Higher entropy indicates more irregular movement pattern, which can signal risk situation like falls or passing out. We combine entropy analysis with other features such as eye closure duration in the visual signals to enhance detection strength and reduce false positives. This multi-sensor integration ensures reliable identification of critical situations. In experiment in results, our statistical analysis confirmed that 5 out of 6 sensor parameters showed significant difference between stand and line posture. AX's acceleration proved to be the most discriminative parameter with very high statistical significance. Entropy analysis revealed that the line post generates high data variability, mean entropy of 1.69 compared to 1.59 when standing, indicate greater possible unpredictability, which is useful for risk detection. For the drone scenes, we activated 18, 18.5% accuracy in detecting prolonged eye closure. However, we identified some false positives in fall detection during abrupt walking movement, which will be addressed with more refined AI algorithms in future works. And compared to previous work, our solution provides significant advances, unlike systems that relies solely on Wi-Fi, which suffer from electromagnetic interference in industrial environments. We use hybrid communication that ensures connectivity even under adverse conditions. Local processing on the helmet reduces latency, which is critical for safety applications. And additionally, our solution use accessible is to implement components making it cost effective and practical for real industrial deployments. In conclusion, uh, we present an integrated IoT solution that combines intelligent sensor, hybrid communication, and entropy-based analysis to improve occupational safety. Our initial results demonstrated the system capability, sorry, for to identify risk situations with suitable response time. The main contribution include the hybrid communication architecture, the hybrid-based detection approach, and a functional prototype validated through controlled experiments. As, as the future works, we plan to expand the system to recognize additional clusters commonly found industrial settings. We will validate the solution in real industrial environments to assess its resilience to electromagnetic interference and test scalability with a multiple device appearing at the same time. We also plan to implement embedded AI models to improve automatic detection of fouls and other risk situations while reduce false positives. So thank you for your attention and I am available for questions.